This is Chapter 14. We're talking about periodic trends. We're on page 2, and we're going to talk about atomic size. And what we're going to look at is the radius of an atom. This is measured in picometers, which is 1 times 10 to the negative 12th meters. We're first going to look at group trends. And group trends, that means it's vertical. So you're going up and down the families. And what happens to the atomic size is it increases as you move down. Let's draw a couple of elements to illustrate why this is. First, we're going to do lithium, which is 1s2, 2s1. So it's going to have, first we're going to have the 3 protons in the nucleus, and then it's going to have 2 principal energy levels. Okay, and then we're going to go to sodium, which is going to have 11 protons in the nucleus and 3 principal energy levels. Okay, now, as we look at lithium going to sodium, we can see that we have added 1 additional principal energy level. Now let's populate these energy levels with electrons. We have 2 electrons in the first principal energy level, 1 in the second, and here we have 2 in the first. We have 8 in the second principal energy level, and 1 electron, the valence electron, in the third principal energy level. Notice that as you go across, or actually if you go down, as you go down from lithium to sodium, sodium is below lithium, you're going to see that the valence electrons are in higher principal energy levels, and thus they are farther from the nucleus. So as you go down a family, you're going to see the atomic size increase. So you see increase atomic radius down the families. Now, let's do the same thing with what happens as we move across a period. And remember, across a period means you're going horizontally across a row. And what happens here is it shrinks as you move across. So this time we're going to go from lithium to neon. We're going to move across a period. So we've got 1s2, 2s1, and we have 1s2, 2s2, 2p6. We're going to have 3 protons in the nucleus of lithium. We're going to have 10 protons in the nucleus of neon. And let's go ahead and draw the Bohr models for these. So we'll draw the nucleus for each. So there's the nucleus for each. And we're going to draw the first principal energy level around lithium. Now, that's the first principal energy level. If we go over to neon, the first principal energy level is going to be much closer to the nucleus because the 2 electrons are feeling the pull of 10 protons here, whereas in lithium, the 2 electrons are only feeling the pull of 3 protons. Now let's go and draw the next energy level out. So we're going to draw the next energy level for lithium. And then let's draw the next one for neon. Again, what you see is that the second principal energy level is much farther away for lithium than it is for neon. Because in the case of neon, the 8 electrons, the 8 valence electrons, are feeling the pull of 10 protons in the nucleus, and there's only the protection of the 2 electrons. So what happens is that you have elements have the same number of energy levels, and shielding electrons. So they both have 2 principal energy levels and 2 shielding electrons. But as you add protons to the nucleus and electrons to the same principal energy level, the effective nuclear charge pulls the outer electrons closer to the nucleus.